Hi, we're Team 20. Our project is called Food Intelligence Services, and we are working for Ocado. On the Ocado website, customers normally have to shop from a wide range of different products, and our aim here is to reduce the number of manually searched ingredients by investigating different methods for producing recipe embeddings that can then be used in recommender systems. So our core requirements are to implement unique models for producing embeddings and optimizing each of them, and then coming up with several evaluation metrics, and then comparing different models using a mutual evaluation metric, and then visualizing this by using a dimensionality reduction technique. During this project, we use various different types of libraries. So we use the Keras library for building convolutional neural networks and artificial neural networks. We use NLTK library for pre-processing, removing stop words and extracting the main ingredient. The Jensen library to provide ingredient and instruction vectors using the word2vec and doc2vec algorithms. sklearn to normalize data during pre-processing or evaluation, and then skipi to find Euclidean distances and cosine proximities in during the evaluation of our models. To evaluate our model, we calculate the mean distance between recipe vectors in each category and then take the average of those distances, and then we call that the alpha Euclidean distance, which is the AED. So we calculate the AED for a trained model, then we calculate the AED for a model that assigns a random vector to each recipe, and then we calculate the accuracy here, which is the 1 minus x over y, and if that came out as 0.8, then we say our model is 80% better than if we had assigned it randomly, if we assigned recipe vectors randomly. The model implemented was the image-to-vec model, which uses a convolutional neural network to predict recipe tags. So we use a convolution layer, then we max pull all of our results from that, and then we flatten it and then put it through a fully connected layer. And this is the visualization for that. Another model implemented was a continuous bag of odds model, where we predict the probability of an ingredient existing given all other ingredients in the recipe. Now, as you can see, this architecture can only take in 3 different ingredient vectors, and we use that to predict one other ingredient in the same recipe by averaging all of those in an average layer. Now, as you can see, this is a visualization. So another model that we implemented is this sort of architecture where ingredient vectors are trained against tags, and for that you can see the visualization for that. And we could also feature cross the ingredients with their quantities, and we tried to implement that as well. We fed in lists of tag lists into the Jensen's word2vec model, and that would give us tag embeddings, and we had to find a way of converting from tag embeddings to multiple recipe embeddings, and we decided to use an autoencoder, and that autoencoder would take in a set of tags, and then the output from one of the intermediate layers. So for example, out of here would be taken as the recipe embeddings, as the recipe embedding for that set of tags. I've also created a tag demonstrator that takes in a set of tags and gives us the top 10 similar tags. So as you can see, I put scones and cakes, and we get muffins, biscuit and cookies, bread, German, maybe it's linked in some way. And here I used tag embeddings to create this. So here's an evaluation of all our models using the alpha Euclidean distance approach that was talked about previously, where we compare how good our models are compared to a random randomized model. So as you can see here, when we train ingredients against tags, it goes up to a point and then it decreases. And we can also see here the auto-encoded tag to vec is way better than all of the models because it uses an autoencoder rather than taking the mean of component embeddings to get the recipe embeddings. To summarize, we've attacked this problem on different fronts. So we've developed different models that take in recipe images, ingredients, quantities, and recipe instructions. And these models would assign meaningful vectors to the recipes that these respective components came from. Furthermore, we have managed to compare our models using a mutual evaluation metric, the alpha Euclidean distance approach, and we've also used dimensionality reduction techniques like TSNE to visualize our models. And we've developed a demonstrator that highlights the quality of one of the models, the tag to vec model.